Hello everyone. In this video, we'll be talking about the problem minimum number of k consecutive bit flips. Now, I'm not going to lie, this is one of the trickier ones, and it took me a while to figure this one out myself. But good thing for you is that I'm here to make it as simple to understand as possible. So without further ado, let's understand what the problem is. So we have been given an array of integers. These integers will either be 0 or 1. Those are the only two values possible for each element. We've been told that this array needs to be converted into one that is full of ones. So each element should become one by the end of it. By the end of what exactly? So they've told us that we can follow a process to do this. They've given us a value k. That k will have an integer value. Let's say it is 3. They say that at one point in time, we can flip three consecutive elements together. What does flipping mean? Flipping means we can convert a 0 to 1 and a 1 to 0. But it has to be three consecutive elements at a time, or k consecutive elements at a time. So let's say we have this window over here. These three can be flipped and turned into 1. Similarly, if this is the window, then this will become a 0, 1, and 0, something like that. And we have to do it in such a manner that the entire array becomes full of ones by the end of it. So what approach can we follow to deal with this? So let's start with the greedy approach. So I've written the algorithm down to save on some time. How does it actually work? Let me dry run it for you. So for every single element, we'll go over them one by one, right? For every single element, we check if this element is 0. We simply flip the elements inside this window. The window consists of three consecutive elements. So this is our window. If current element is 0, we flip, turn all of them to their flipped counterpart. And then we move forward to the next element. And of course, we keep track of the number of flips we are doing, right? So our answer at this moment is 1. We move forward. If the current element is 1, since we flipped this has become 1, we simply move forward to the next one. We get a 1, move forward, again, move forward. We get a 0 once again. So we have to take this window, flip the elements over here. This becomes 1, this becomes 0, this becomes 0, and our answer now has two flips as part of it. Then we move forward once again. We are pointing to this element over here. It is a 0, so we flip. This becomes 1, this becomes 1, this becomes 1. And our answer becomes 3. And we don't have any more flips to perform because all the elements over here are 1. What if it was a case where this 1 did not exist? In that case, it's very simple. Once we reach over here, we would see that this window, which had a 0 over here, that 0 over here, and this is where we end, right? So let's say we flipped, we have two zeros, but we need to flip these two to turn them into 1, but we don't have this third element to flip alongside them, right? There's nothing over here. In that case, our array cannot be converted into an array of ones. That is when we return -1 as our answer. Alright, so that's the greedy approach. The time complexity of it is big O of n into k. N because we go through every element once, and k because every flip is performed on k elements at a time. Alright, and space complexity remains constant because we don't allocate any extra space for this solution. And that's the greedy approach. Can we do something better? Yes, we can. For that, we will be using a queue. So let me bring that algorithm up for you. So in this approach, we use a queue to our advantage. Why do we follow this approach in the first place? In the previous approach, we were flipping the elements every single time, right? We were turning them from 0 to 1 or 1 to 0. So the complexity became n into k, big O of n into k. We want to avoid that factor of k over here. So we'll not actually be flipping the bits this time, but we'll be using some sort of mathematics to our advantage. by the help of a queue, with the help of a queue. So here, let's start off very simply. Okay, let's not worry about this entire thing. We'll start off very simply over here. And for every element, let's not worry about this part yet. For every element, we have to check, does the current element need to be flipped? Does it need to be flipped? It is a 0. It, of course, needs to be turned into a 1 to get our answer. So, yes. Can we? Which basically means, does the window starting from this element exist? The answer is yes. We can cover 3 elements starting from this window. So, we can flip this element. So, we add the current index to our queue. We'll see why in a bit. Just add it to the queue. And of course, increment your answer from 0 to 1. Then we move forward. Okay, so at index 1, we have to now perform this algorithm again. And I made a small correction here. We'll get to it. So we check for valid flips for the current element. What does that mean? I say that we are sorted till here, right? Everything before the current element is sorted. But because a flip may have been performed in this area right before the current element, we need to check how many valid flips have been performed on this current element. Could be 1, could be 2, could be 3, could be any number, right? Depending on the value of k. So we have to check how many valid flips have been performed for the current element to assess its actual value, right? Whether it is a 0, whether it has been flipped to a 1, or whether it has been flipped again and turned into a 0 once again, right? We have to check all these cases. So we have to check for the valid flips for the current element. How do we do that? We use this formula. So while our current element at index I, while this is beyond the range of influence of this element. I use some heavy terms here. Range of influence. What does that mean? That means that Q0, which is this element over here, plus K minus 1 is the range of influence of this particular index. By that, putting it very simply, it means we performed a flip on index 0, right? What is its range of influence? 0, 1, and 2. These are the elements that have been influenced by flipping in this window at index 0. Now, I greater than this range of influence, but that basically means, is our current element not affected by the flip performed at this index over here, which is 0 in this case. Greater than, that is what it implies. If is I greater than this range of influence? If it is, then we remove the value over here. And then we keep repeating the process till this case is valid. But right now, in this case, that is not true. This I is not greater than this particular value, because Q0 is 0 plus K minus 1. So 0 plus 3 minus 1 gives us 2. Is 1 greater than 2? No, it is not. This is index 1, right? So we move forward to the next part of the algorithm. Does our current element need to be flipped? Now we can see virtually that this value is actually supposed to be 1, right? So do we need to flip it? No, we do not. But when we're actually typing the implementation out, how do we check if this current implementation needs to be flipped? So if this current element needs to be flipped. For that, we have two cases. Now this element, its original value, the one in white, it could either be a 0 or it could be 1. Now we have to check whether this has been flipped or not. Does it need to be flipped or not? When would it not need to be flipped? When the value, current value, the one in green, is 1. Because we are looking to turn it into a 1, right? If it is 1, we don't flip it again. If it is 0, we flip it. So how do we calculate the actual value, the one in green? The actual value can be calculated very simply. The formula for that is simply length of this queue, let's call it L, modulus 2. That tells us whether the current element has been flipped or not. By how does this formula work exactly? Well, this operation that we performed right in the beginning, that we'll continue to perform for the next iterations, has given us the length of the queue in such a manner that the length of the queue represents the number of times this element has been flipped. Try to pause, try to think about it, right? At index 0, we performed a flip that did influence this element over here. It did manage to flip it. So we count it. Anything else is discarded from the queue. So this length is only of the valid flips for this current element. So the number of times it has been flipped is represented by this length. And now we want to check whether this value has been flipped or whether it has been flipped again to make it the original value. Basically, if you have a 0, if it has been flipped to a 1, if it has been flipped to a 1 and then flipped again to a 0, we want to calculate that. So that is what the modulus operator is for, mod 2. That is what we're doing it for. So if this length is 1, 1 mod 2 would give us 1, which would imply that the element has been flipped successfully. So 0 has become 1 or 1 has become 0. But if this length is let's say 0 or 4 or 2, and let's call it 2 for now, then 2 mod 2 or 4 mod 2 or 6 mod 2, any even number, that would give us a 0. That would imply that either a flip has not been performed on this element or a flip has been performed multiple times, which has reverted it to its original value. So 0 has become 0 again, 1 has become 1 again, something like that. Alright, that is what we're dealing with over here. So if the current element is 0 and a flip has been performed, if this if L mod 2 is 1, a flip has been performed, then we don't do anything. If the current element is 1 and a flip has been performed, then we must flip it again. Because, well, 1 has been flipped. It has been turned into a 0. We need to turn it to 1 again, right? So that is when we perform a flip. But if the current element is 0 and the flip has not been performed, or if it is become 0 again, basically, this f is basically L minus L modulus 2. If the current element is 0 and a flip has not been performed, then we must flip it again, right? But if the element is 1 and the flip has not been performed, we don't do anything because we want the value to stay as 1. So these are the two cases where we actually flip. Does the current element need to be flipped? That is when we check. That is what we check now. So current element is 0. Its current original value is 0. The current value is now 1, right? You can check it with this formula. Does it need to be flipped? No, it does not. So we move on. Now we check for valid flips for the current element. So 0 plus k minus 1 is still 2, right? So I is 2. It is not greater than this value, which is also 2. So we move forward. Does current element need to be flipped? Its virtual value is 1, right? Because 1 mod 2 is basically 1, which means the element has been flipped already. Like its original value is 0 and it has been flipped. So we don't do anything. We move forward. Now, now we check again. We check for the valid flips for the current element. We have this 0 over here. So 0 plus k minus 1 gives us 2, but I is 3 right now. So we have to remove this index from our queue. So we will delete this element, we pop it, we remove it. Alright. Then we move forward. Does the current element need to be flipped? Its original value, I should write it as original value over here instead of current. Is its original value is 1, right? And the length of the queue is 0, which would give us 0 as our answer over here. That if is this value flipped? No, it is not flipped. So original value is 1 and it is not flipped, so we don't do anything because we wanted to stay it that way. Move forward. We check for valid flips in the current element, but since our queue is pretty much empty, we don't do anything about it. We move forward. Does current element need to be flipped? Its original value is 0. And is it flipped? Well, we don't have anything in our queue, so it is not flipped, right? It has been flipped 0 times, which is the length of the queue. So 0 is the original value. 0 is the number of times it has been flipped, which means we need to flip it once to turn it into 1. So what we do now is check, can we do this? Yes, we can, because this window allows us to do so. So we add our current index to the queue. So we have 4 as the current index, and we are performing a flip over here, so we increment this value by 1. And of course, we move forward. All right. Now, this is an important case. Check for valid flips for the current item. Now, this is very repetitive, but this repetition is necessary to understand what we're dealing with. So we check for valid flips for the current element. This I is 5 right now, right? So we have 5, 6, and 7. So this 5 is it greater than this value over here, which is 4? Q0 is 4, right? 4 plus 3 minus 1, that gives us 6. Is 5 greater than 6? No, it is not. So we do not remove the index. Does the current element need to be flipped? Its original value is 1. So it is either this case or this case. So the length of the queue is 1, which means the element has been flipped. It is odd, right? So odd means the element has been flipped once. It was basically flipped at index 4, right? So its virtual value, let me just write that down, is actually 0. And so is this one. This has been turned into 1 virtually. So we have the original value as 1 and it has been flipped. So we need to flip it again because it was flipped to 0. Now we need to flip it back to 1. So we simply add the current index to our queue like this and we increment over here. Now, of course, the virtual values now would be something like this. After this flip, this would become 1 and this would become 1 as well because this is the window we are dealing with. Move forward. All right. We check for valid flips for the current element. So is 4. Is the flip that we formed at index 4, does it influence this element over here? We can see that it does, but let's calculate it mathematically just to be sure. So we have 6 as I. We have 4 plus 3 minus 1, that is 7. 6 is not greater than 7, so we don't remove anything. Does the current element need to be flipped? We can see that it does not need to be flipped, but we check just for sanity given our approach that we're discussing. So the original value is 1. The length is 2. 2 mod 2 gives us 0, which means that the value has essentially not been flipped or it has been reverted. So we have this case over here, which basically means that we don't need to do anything. We have to simply move forward. Now, We check for valid flips for this one over here. This index has incremented to 7. 7 is still not greater than 7. So we basically, oh sorry, this is 6. My bad, my bad. There's a small correction over here. This is actually supposed to be 6. But that does not make a difference because the previous index was 6. So we are safe. But in this iteration, that would have caused a problem because 7 is now greater than 6, which means we have to remove this element from our queue. And then we check the same for 5. So 5 plus 3 minus 1 gives us 7. So 7 is not greater than 7. So we retain this index in our queue. Does the current element need to be flipped? We can see that it does not. To be sure, we check the original value. It is 0. The original value is 0. And has it been flipped? The length is 1. 1 mod 2 gives us 1, which means it has been flipped. So it has been, original value is 0. It has been flipped. So we don't take any action because that is exactly what we want. So we simply move forward, and there is nowhere to move forward now, right? We are out of this array. So we simply return our answer, that is 3. That is the approach that we use with a queue. Now the time complexity is big O of n. The space complexity will go up to big O of k, I think, because at any given point, we will not have more than k elements inside our queue. Now, can we reduce this space complexity somehow? Yes, we can. And we will do that by removing the queue from our equation. Now you say, you have removed the queue. How will we check if the element has been flipped or not? We will track that in a variable. Let's call that variable valid flip count. Valid simply means that the flip count should be valid for the current element only, not globally. Alright. So if we add this element, how many times has this element been flipped? That is stored in this variable, which will first start off at 0. Along with that, what we'll do now is we will, instead of storing our index inside the queue, we will modify the original array, and let's say we'll assign it a value which could be 2. So if we perform a flip over here, just focus on the white writings for now, which are the original values. If we're performing a flip over here, then we will mark it as 2. We'll change the value. Alright. We'll move forward. Then we'll check for the valid flips for the current element. And of course, this will increase with 1 by 1. And we'll check. Of course, this condition will change. And it will become something like this. Let me walk you through it. So, uh, and it will become something like this. So, let me walk you through it. We check for every element if it is greater than the length of the window, and that is just to handle any edge cases. Don't worry about this one so much right now. We mainly focus on this one right here. If the element at I minus k is equal to 2, what does that mean? If we are, let's say, over here, if the element at I minus k is 3, right? So 0, 1, 2, 3. 3 minus 3 would be 0. If this element is 2, which is true in our case, we reduce the valid flip count by 1. Why do we do that? Because this flip performed at index 0 is only affecting this window. So when we reach over here, this flip is not valid for us anymore. Only flips starting from here are valid. Alright, that is the logic behind this. So we reduce the valid flip count, and valid flip count simply is the replacement for this length mod 2 that we had over there. The rest of it will remain very, very similar. So we check the current element. Does it need to be flipped? Well, if the valid flip count is 1, then if the valid flip count mod 2, right, this L will be replaced by valid flip count. If mod 2 is 1, then we do what we did previously. If it is 0, then we also do what we did previously. The rest of it will remain the same. All right, very, very, very similar. And of course, this would change because we won't have anything to add to the queue. Instead, we will increment the valid flip count by 1 in this case, and the rest of it will remain identical. This would save us on a bit of space. So if k is very, very large in a large system, this would mean a lot. So that is basically how you solve the question minimum number of k consecutive bit flips. In the next video, we'll be implementing it. So stay tuned and follow for more.